Ok, so, bon, ben, bonjour à toutes et bonjour à tous. Aujourd'hui, nous allons avoir le plaisir d'accueillir Ruben Zakine qui a fait sa thèse à MSC. Et je pense qu'il va nous parler de choses liées à ça. Et il a fait ensuite un postdoc au Quant Institute à New York et actuellement il est dans un second postdoc, donc au LEDX, dans la chaire d'éconophysics et des systèmes complexes. Ça?
Yes, oui, tout à fait.
Bon, ben, à
Ok.
toi.
Bon, bah, merci beaucoup. Thank you very much. I do it in English if everyone is okay. I mean, if it's better for non-French speaker. Okay, today I'm going to talk about the elusive surface tension of active fluids. I'm going to define all the terms of the topics, of course, and very rapidly I can summarize my research interest. So I basically come from soft matter and statistical physics. I'm interested in biomimetic systems and hydrodynamic descriptions of these biomimetic systems. At Laboratoire MSc, Material System Complex, I mainly worked on, I would say, surface tension and active matter. Then at NYU, I worked on biomimetic systems and small-scale transport, and also studied tools to compute relevance in dynamical system and hydrodynamic systems. And more recently, I tried to apply these tools from hydrodynamics and statistical physics to ecosystems and socio-economic systems. And today, we are going to talk about the elusive surface tension of active fluids, which is a work that was done in joint collaboration with many people. So the main collaborator is Yongfeng Zhao, who did mainly the big simulation with many particles. Milos Knežević, who was at Cambridge at the time. Adrien Der, Julien Tailleur, and Frédéric van Vigeland are at Laboratoire MSc, and Yariv Kafri is a researcher at the Technion in Haifa. So, the motivation of this work, let's start with the beginning. So, there's, let's say, these last 20 years, there's an upsurge of studies, of research about these systems, strange systems of collections of particles or agents like bacteria, sheep, birds, or self-propelled colloids, like synthetic matter, that somehow inject momentum and energy in the system at the microscopic level. And because of that, we call that active matter. It means that the system is out of equilibrium. It is driven out of equilibrium by the constituents themselves, and it's not at all like a pan on the fire or a boiling stuff, right? Where the out of equilibriumness comes from outside of the system. Here, it really comes from the constituents themselves. Okay, and so I won't dive into the interactions between the constituents, but what you see in these different systems is that you can have phase transitions or condensation of these agents. For instance, in bacteria colonies, here you have in red and green, you have two different colonies that aggregate in this funny pattern, okay? And we would like to understand what drives the condensation and can we describe the condensation? And when you have this kind of condensation, you want to study the interfaces to see if the condensation is stable. And a generic tool to study interfaces at equilibrium is surface tension. And the question we have is it a relevant observable out of equilibrium in these active matter or active fluids systems? What is interesting also is that, okay, you have this liquid condensation, you can study it far from any boundary, but now when you want to modify or if you want to guide the matter in some channel, I would say, you need to understand what is the behavior between this matter and the channel, and so you need to understand what's happening at the boundaries, and typically you end up with the question of a triple line surface tension and what's happening at the interface between liquid, gas, and solid. And so this motivates the work of surface tension of these funny liquids. Okay, so I'm going to list the definitions of what could be a good surface tension, what could be a good observable, a tool that will allow us to predict interesting stuff about the interfaces. So surface tension should predict the stability of the interface of the fluid we study. It should maybe correct the pressure differences for a curved interface, which is what we call the Young-Laplace pressure. Okay, and what we would like also is that it would quantify partial wetting, which is the Young-Dupré law. It tells you the angle of wetting. It tells you if on a given substrate your matter is going to fully wet, okay, and spread to the end or to the edge of the solid. And also you would like that this observable, which is surface tension, is an intrinsic property of the interface, that it does not depend on what's happening very far out the boundary. And this is a tricky point because in these systems that I show, these matter are self-propelled more often, and you could have macroscopic currents that dress the measurements of surface tension. So we will come back to that later. So what is the problem with surface tension is that you have many definitions in equilibrium, let's say. And you can start from a definition with the free energy, what it is. So you have let's say a fluid, you have a deformation of this fluid, of this cubic, I don't know, the cubic cell of this fluid. And you know that the surface tension is basically the derivative of the free energy with respect to the change of area by keeping the volume constant. And so the surface tension is a free energy per unit area. And this works very well to describe droplets, okay? But here in these systems, there is no free energy because we keep injecting momentum and there is dissipation at the microscopic level. So you cannot have a global macroscopic free energy that takes into account what's happening in the dissipation. I mean, it's not conserved. Another candidate would be, for instance, if you have here an interface between a fluid A and a fluid B, you write down the possible the Hamiltonian of the fluctuations of the behavior of the height, which is here, and you know that the surface tension is the coefficient in front of the quadratic term here when you do a Landau expansion of your height, just a gradient expansion. And so at the lab, you can look at this observable, which is the correlation of the height. Okay, you take the Fourier transform, you look at the spectrum of the correlation. And you know that this spectrum of the fluctuations is related to surface tension in that way, with Q, the Fourier mode. And when Q goes to 0, which means when you look at large scales fluctuations, then you know that you recover surface tension. The problem is that here again, well, the KBT is not defined because the fluctuations, you don't know how they are related to temperature in your system. When you put a probe and try to measure the diffusion of particles, this is not related to temperature. You don't have a fluctuation dissipation theorem, you don't know. So basically, keep in mind that temperature is not defined in these systems. So this energetic approach is not very good so far. So let's go back maybe let's go back to a force measurement, okay? Because you now remember that surface tension is a free energy per unit area, but it's also a force per unit length. And a force, this we can measure. Whatever the system, it doesn't rely on the free energy. So just like pressure is a force per unit area, surface tension is a force per unit length. And so these people try to first understand if this description for pressure, at least, was relevant. And so they considered this model, very simplified model of active matter systems. These are small self-propelled disks, okay? They go in straight line with some velocity v0, and the orientation can diffuse, okay? They can rotate slowly. And when you put this, a lot of these particles in a container like that, and you put a wall in between, you don't have necessarily the same wall on the right and on the left, and the pressure equilibrates, which means that it's the same force on the right and on the left, which means that it is indeed relevant to consider pressure as a force per unit area. And since it's relevant for pressure, it might be also a good, it's a good maybe clue that it might be relevant for surface tension. Okay, so what I'm going to consider in the following is these particles, okay? So it's very, it's a tool to model these active systems. These are particles with their position Ri. They are self-propelled. They interact with the walls. Okay, we are going to consider interactions with the boundaries. It is important, and they interact only repulsively with each other. Okay, and in these systems, what is interesting is that without any attractive interactions, they end up with this kind of condensation here. What you see in the dark blue region, you have condensation of these particles without any attractive interactions. It is because of the self-propulsion. When two particles collide, there is time for another one to collide also, and you have like that effective attractive interactions. But in the beginning, there is no attractive interaction between the particles. And this effective attractive interactions leads to this phase separation like this between a gas and a liquid. And this is what we want to study, the phase separation between a gas, a liquid that are in contact with a solid boundary. And so this model will allow us to probe what's happening at the walls. Okay, it's I would say the not vanilla, but the typical active system, active fluid that is considered in the literature for many years now. And you see in these experiments that if you take different confining walls, so here I put a potential, a confining potential V1 here for the wall at the top and the bottom, and a different wall more stiff on the right and on the left with a different color. And you see that the wetting is different here and here. Yes? Yes, no, the angle just follows a Brownian motion, which means that in the end, the particle just does something like this. It is self-propelled, but it diffuses, you see. The orientation changes, and it's self-propelled with a constant velocity, but the direction changes. Yeah, it's random. The direction is random. And you have collisions. You have only repulsive interactions between particles, hardcore repulsive interactions. Yes? Just by the density. So here it's light. Yes, exactly. No, it's not. I mean, you need to have a bulk, which means that you need to have a plateau of density here. So you measure you put little boxes in your simulation. You measure the density when it's a plateau, which is I mean, so it's constant, and here it's a lower value, and the interface is basically defined as the middle, the midpoint between these two densities. No, I mean, you have in both cases you have, it's just that the fluctuations are not the same for a liquid and for a solid. For a solid, the density no longer fluctuates, and for liquid you have fluctuations of the density. Yes, it depends on the density and on the propulsion speed. But indeed, it's not easy to explain. I mean, they took a long time to really understand this. Well, they only repulse. It's a hardcore. It's a hardcore interaction. So they only repulse when they touch. Okay. So it's not a Coulomb interaction where they feel each other very far away. And the picture is that when you have two particles colliding, okay, there is some inertia in the angle, in the diffusion of the angle. So they collide, and before they separate, there is a third one that comes into group of particles, and a fourth one, a fifth one, and this is how, when the density is large, you can have this condensation of particles. Yes? Yeah.
But we're all pointing in almost the same direction. So in your case, the theta is completely independent on anything else. It's just standard.
The theta of each particle has an orientation which is proper to the particle, and this orientation is random.
And it's never,
But it's continuously changing. Okay.
So
Pure Brownian noise, Gaussian random Brownian noise.
what does it get as in your equation, the potential?
Here, in the force exerted by the wall on the particle I. It's just that this force here, I can write it as the minus the gradient of a potential.
Okay.
Okay. You can take any potential you want, quadratic, Lennard-Jones, whatever. Yeah, at some point you need a separation of scales. You need that the repulsion of the potential is smaller than the typical length of the particle of diffusion of particles to really split between the different lengths. Yeah. Okay. So with that, we're going to start to measure or to consider the fluid-solid surface tension. Okay, so to measure the fluid-solid surface tension, we were inspired by the Langmuir-Blodgett method, which is what exactly? So you have a floater between, at the surface of a fluid, and on one side, so you put the floater. It's these two compartments are not communicating, and on one side you put some surfactants or anything that you want, and since the fluid is not exactly the same on the left and on the right, you have a net force on the floater. You have to imagine that it is transverse in this direction. Okay, so the force is exerted all along the floater, which is perpendicular to this plane. And so the total force on the floater is basically the difference of surface tension here when the fluid touches times the length of the floater. Okay. And our version of the Langmuir-Blodgett method is basically the same. It's just that instead we are going to put a fluid here in the container, and the interface in blue and in red are now replaced by material 1 and material 2. Two walls, okay, made of different potentials. And there is a junction between these two. And the junction plays the role of the floater. And since I will no longer talk about the transverse direction, I will just say that the force is equal to the difference of surface tension. Okay, I get rid of this floater length. And so in the end, what is interesting is that the force that you measure, the tangential force that you measure on the junction or on the wall that is allowed to move is the difference of surface tension. Okay? So this should absolutely work in equilibrium because all the theorems we have say that it should work. There are many experiments that show that it works. And indeed, we can check that. When you look at the free energy, when you go back to the definition with the free energy, the fluid in contact with the material 1 has some free energy, gamma 1 times the length in contact. The fluid in contact with material 2 has the same kind of energy, but now proportional to the length of interface between the two. And the free energy associated to the junction that we don't need, but we know that it's constant. Okay. And when you take the derivative with respect to L1, to the length, this gives you access to the force. And this is, when you do the computation, it's just gamma 2 minus gamma 1. And the free energy associated to the junction disappears because anywhere you are in the fluid, this term is constant. And it says that it confirms that the details at the junction are irrelevant in equilibrium. So we are going to see that it's not the case out of equilibrium. So let's be more precise on the model. As I said, we have a wall with some stiffness V1 that repels strongly a particle, a force with some stiffness V2, or a potential V2, which is, you see, less stiff than the blue one, and repels less the particle here in gray. And the width, the junction has some width, W, that interpolates continuously between the stiffness of the wall V1 and the stiffness of the wall V2. And you do the simulations, and you see that for equilibrium particles, indeed, when you plot the force with respect to the junction width, it's absolutely constant. But when you do that with self-propelled particles, the force changes with the width of the junction. So there is something more somehow in your that you catch in your system because it depends on the details of the junction. And we are going to try to understand what is that we catch here that changes the force that we measure tangentially. So the goal is to compute basically the force. I mean, it's the only way where we can have a tangential force, because here, far here, the wall is translationally invariant, so you cannot have any tangential force. Here the same, but at the junction you interpolate between the two, so you have kind of a ratchet, let's say. Okay? And so our goal is to compute the total force exerted by the particles, F by the particles, on the wall, on the box that catches the junction. And so this is the discrete way to write it, and the continuous way is just simply to write that we just have to know the density of particles times the minus the force exerted by the junction on the particles. Okay, so this is, I mean, rapidly. So you start from the macroscopic equation that you can derive knowing the motion of all the particles and knowing the interaction between the particles. It's a continuous equation. Of course, the number of particles is conserved. So, I mean, the mass is conserved. So you have no choice but to have this divergence equation, okay? And the flux, you know it. It's R dot times the particles. I mean, where they are, that have the particles. And what you want to get is to isolate the force density and then sum over this force density on the box. So you do that, you do a small computations, and you end up with these two terms. You find out that the total force density is the sum of the local orientation of your active fluid and a weird term, okay, which is something that is proportional also to a force density, but which is what we interpret as a drag, and I will come back to it in the next slide. And then you integrate and you have the access to the force. And so finally, what you have is this, is that the force that you measure is indeed the difference between two surface tensions that you can measure independently and that are indeed intrinsic properties of the interface of the active fluid and the material, but also another contribution that really comes from the drag exerted by the particles on the substrate and on the solid close to the junction. And this comes from, I mean, this drag is really because the particles are self-propelled and they dissipate energy into the medium. And so you necessarily catch the drag when you measure this tangential force. When you plot this flow, and I mean, a posteriori, you really understand what's happening because it's, as I said, it's a ratchet. It means that if the wall is strongly repulsive here, particles that come here, they are going to slide like that and enter. I mean, since this one is softer, they're going to enter in this one and going to be expelled far away. And in the end, macroscopically, what's happening is that you have these recirculations because of the self-propelled particles. So a priori, you cannot get rid of these currents. Maybe what you can do at least, or you can try to do, is to take a very long width. Someone had a question? No. Okay. You can take a very long width so that you minimize somehow the ratchet length, and minimize these macroscopic currents. This is an option. Another option is to take geometries of the system that get rid of these currents. So let's look at the spherical geometry, where you know that you cannot have any currents because it's isotropic. And you can play the same game and compute the total force exerted by the particles on the wall. And what you find out is that the total force at a radius r is the pressure, the total pressure, because then you divide by the total surface of the container, is the bulk pressure inside plus a correction, and you recover here the Young-Laplace correction. So you're very happy with this geometry, but you see that as soon as you want to get rid of currents, the surface tension is very hard to measure because it's a sub-extensive contribution. So yes. No, you don't need you don't need two materials in this case. Only one material. Well, so here's another setup, just to finish on that. This is another setup where you can measure the force. Okay, you have a container, a wall that measures, and when you measure the force, what do you measure? You measure the pressure force and also the force associated to the junction over there. Okay, and so you have what you catch when you measure the force is both the pressure times the length or the surface of your piston minus 2 times the surface tension. But in both setups, you see that you cannot get rid of the extensive contribution, which is the pressure. This you see, I don't know if I'm clear enough, but I mean, maybe it's a thought experiment. It's just that you have nice geometries where you suppress currents, but what you lose is the fact that you can directly access easily to the surface tension because they are sub-extensive contributions. Yes? Yes. Where? Here? Yes. So I actually have a net flow, but it doesn't address the measurement of surface tension, but because it's very localized here. Yes. Okay. Okay. I will do a small recap at this stage. It seems that we have an interesting definition for the surface tension, at least for a fluid solid boundary, and that we are able to measure the total force on the tangential force on the plate as the difference of surface tension plus a drag force that is necessarily here because of this dissipation of this active matter. These currents are due to activity, and so it seems that this surface tension is a good candidate. And so with that, we're going to dive into this maybe more involved setup, which is trying to measure the liquid gas surface tension, and we will end up with trying to mix everyone and trying to recover the Young-Dupré law for surface tension. No questions so far? Okay, and so here is a small question for the audience. How do you measure surface tension between a liquid and its vapor in the lab? I don't know, there are many ways, but do you have one candidate in mind? Yeah, okay. So pending drop works. Okay. Yes, I had this one's. This one works. The Denouille ring. No, how do you call it? No, I think it's tensiomètre de Denouille. No, I don't. I think, but it's so. This one is the circular isotropic version of the Villelmy plate experiment. I don't know if you have it in mind, but it's exactly that. That you dip a plate in a fluid, you pull out this plate, and the difference of forces that you measure when the liquid breaks, when the meniscus breaks, is exactly 2 times the surface tension times the length here that you have in contact. And the key in this kind of experiment is to take a wetting, I mean a solid that is completely wet by the liquid, so that what you measure is only what's happening here between the liquid and the vapor, and you don't catch what's happening between the solid and the liquid, because the interface here won't change when you pull. So you only catch the behavior between the liquid and the vapor. Okay. So this is So this is what I said, that the key is to only probe the liquid gas tension and not the solid gas and solid liquid tensions. So this is what we do in silico, let's say. So we have your liquid, your active liquid here in gray, here your active gas in a lighter gray. So you have a phase separation between your active liquid and active gas. And then you put a probe, which is just like the Villelmy plate. You put a probe at the interface and you wait for the liquid to completely wet the probe. And then you measure the force on the probe by the liquid. And the funny stuff is that the force that you measure is negative. And which means that in this geometry, it means that the plate is expelled from the liquid. And in other words, it means that the surface tension is negative. Okay? But the interface is stable. So there is a small paradox here. And this paradox is just because, in fact, we all have in mind the picture that a negative surface tension leads to an unstable interface. But because we rely on an energetic picture, where you think about it's favorable to create interface when the surface tension is negative. But here you don't have the energetic picture. So there is no contradiction at all in this picture to have a negative surface tension and a stable interface. It just means that mechanically, when you put an object at the interface, it will be expelled. Okay? It's a bit weird, but it works. So just to be sure, we're going to compute and do the same exercise as before. We're going to look at what's happening on a small box around the probe and compute the total force exerted by the liquid on the probe. And so when you do that, you find out, so you have to be careful and take into account the angle here, because it will give you a correction due to Laplace pressure. So you have these two terms here that you would get in equilibrium, and that tell you that indeed you catch the liquid gas surface tension, and once again the drag that necessarily appears when you break isotropy in your system. And when you plot that, and this is what is shown here. When here it's positive, but I think it's minus the. Where is it? The term that you're interested in is this one. Anyway, believe me, just that here you see positive numbers, but the force is definitely negative in this geometry. You do recover that the total force is the sum of all these terms, and the leading contribution is indeed the one from surface tension. And in the end, what you find is that surface tension is indeed negative, which means that mechanically you expelled an object from the interface. And this graph is to show that when you increase the length scale, the mean free, how do I put it? The run length of the particle, which is the velocity time the typical time of a change of direction. When you increase this, so this is the persistent length, yes, you also increase the surface tension, the negativity of surface tension. Yes? Yes?
The orientation is
Isotropic.
isotropic.
In the bulk of each phase, as you see here, it's always isotropic. Yeah. Yes.
This polarization gives rise because over there we see the polarization, the orientation of the agents.
Yes.
And this leads to a net flow.
This is
lead to a net flow, but
yes.
not have a net flow.
It leads to a net flow, which is not, which gives rise to the drag. Exactly. Yeah. And so now that we have all these tools at hand, we are going to try to recover the Young-Dupré law and try to understand how this kind of active liquid spread on a wall. So this is what we're trying to. So this is the setup. You have the setup of I showed earlier. You have the gas in contact with the liquid, and you want to play the same game as earlier. You compute the total force at the boundary here, trying to understand what are the different contributions that you catch from the interfaces. So you would expect a contribution from the solid and the liquid, the solid and the gas, and a contribution from the liquid and the gas. So you write down all the equations, and you find exactly. I mean, the interface doesn't move, so here you have 0, and then you have all the contributions. And once again, if you only look at these terms, you exactly recover your Young-Dupré law with the Laplace contribution, because you have to be careful with the difference of pressure on the right and on the left, because you have a curved interface. And then, because of activity, you get this drag. And just to show physically why it is very important to consider this drag, is that you can actually predict the interface, the shape of the interface, when you put back the drag. So this is the equation of the interface. In red is exactly, I mean, it is what we predict once we measure the drag. So you have to access the drag in your system to get the shape of the interface. If somehow you would like to put a 0 drag in your system, and you say, okay, it's like a passive system, and let's put a 0 drag in this equation. This is in green, this is the interface that you predict. So you are completely out of the picture. And a way to see it is that somehow so there's an interplay between the currents and the shape of the interface. And the way I see it is that the currents themselves stabilize the interface, or the shape of the interface. Okay, questions? No? And so, yeah, I have a few minutes left. So, yes. Yeah, no, what I wanted to insist on is that the fact that the tension is negative is not a problem. It doesn't predict the stability or not of the interface, okay? Because we are out of equilibrium, and so we have to rely on the forces and not on the energy. The candidates we have, they do correct pressure differences. They also quantify wetting and partial wetting, but you have to take into account the drag, and this is what I say, that currents always dress your measurements, and you have to be careful when you look at them. And I will maybe conclude with other systems and open on other systems. Small interlude. Yeah, what's happening when you no longer have these pairwise forces between your particles, or you have different shapes, or a very interesting setup is to look at these quorum sensing bacteria. I don't know if you're familiar with that bacteria that they don't interact directly with each other, with one another, but they interact through the sensing of a chemical in the medium. And so in these kind of systems, which is, I mean, there's a lot, plethora of these systems in nature, there is no forces between the bacteria, or no direct forces. And because of that, there are sources of momentum and sinks of momentum that break the global balance of momentum in your equation. And this description has to be modified. And I won't dive much into it. And before talking about that, no, I wanted to say something else. Yeah, everything what I said applies for systems where the momentum is conserved. So for hydrodynamic systems, or bacteria, or chlamydomonas, or stuff like that in hydrodynamics, in a liquid, it should work because the momentum is conserved. You can at each time rely on the force exerted by the medium on the bacteria and the force exerted by the bacteria on the medium, and you have interactions developing, hydrodynamic interactions, but it's not a big deal. You do have conservation of momentum in the system. Here, when you have quorum sensing, you will no longer have Newton's third law. You don't have action-reaction here. So, and I would like to end with this, the relevant approach that usually people have in statistical physics when they want to find hydrodynamics description of these systems. So it's a bit, yeah, okay, it's a small summary of the philosophy of what we do in statistical physics for the systems. It's what we call a top-to-bottom approach. Okay, you don't know the details of what's happening, but you try to guess the symmetry and the relevant observables. So let's say that density is important in the system, or polarization of the field is important, and you are going to write down the Hamiltonian or the hydrodynamic equation that keep these observables. And then you perform a gradient expansion, keeping only the terms that you think they are relevant in your equation, and you keep symmetry surviving terms, the one that you really believe that they should be here. You make some predictions, and you pray that someday it would be relevant for some systems. Okay, so this is the typical approach in theoretical statistical physics, and I would like to end up with this small description for the density field. For what I told, you know that the number of particles in the system is conserved. So you know that the hydrodynamic equation for the density must have this form here. Okay, you have no choice. You have local conservation of mass. And the current, most of the time, you know that it is the gradient of the chemical potential. The mobility might change depending on the density. Okay, so you know also that the current has this shape. It's a given. You don't have the choice but to put these terms. The mobility is typically proportional to rho. It means that when there is no particles, you cannot have any fluxes. And you have a chemical potential, and this one you expand in gradients. So this is a complicated equation, but it's not. What is important is that you only retain the leading order terms you see of the gradients, and in the end, you know, you don't have the choice. You know the shape of the equation for this kind of systems, and this is very, very generic. And this works. This description works tremendously well, and also for experimental systems. Where you predict here the interactions between two colonies of bacteria that interact like this. I won't spend much time on that. Just to say that, as I said, out of equilibrium. So I presented one way of defining surface tension. There are other candidates, and what is interesting is that all these surface tensions out of equilibrium, they are not the same. They don't play the role. They don't play the same role to predict the capillary waves, to predict Oswald ripening. They all must be used in a different setup, but it's just that in equilibrium, all these definitions of surface tension, they collapse, as you expect. You don't have the choice, but there's only one number that explains the physics of everything. And with that, I will conclude, maybe saying also that, that this is a real important topic. Now that we have the tools to describe this active matter, we would like to understand what's happening when you put them in confining walls, or to guide this active matter. And I thank you very much for your attention.
Thank you very much for your presentation. Some question in the audience? Question?
I have one for the first part. When you show the mean currents, can you show them again? It's for the first setup. Yes, these ones. So, would you have these currents at equilibrium?
No.
Okay. And then how do you, what's the microscopic picture to explain the force? In this case, if you don't have any mean currents, I fail to see how you would have a force, but you do have a force.
Ah, you mean just the difference of surface tensions?
Yes.
Okay. Well, in average, you do have, even though the junction doesn't move, you would have some accumulation at some point in a passive system.
Okay.
Okay. So you have a stationary density that
Yes.
exerts a stationary force on the system, but without any current. No, I'm not clear enough. No, but I agree. It's a good question.
So I guess in statistically the particles must hit the wall with a given angle to yield force in this system? Or
No,
if it's perfectly isotropic at any place, then you will not...
no, it's not perfectly isotropic. I mean, anyway, as soon as you have a boundary, you break isotropy. So the density, when you look at the density of particles in a passive system, it's not homogeneous. You know that you will have some accumulation at the wall, or you have some stationary density which is not homogeneous, but you don't have currents. You don't have macroscopic currents, even though it's not homogeneous. Okay.
Also, thank you. Also on this very picture. So don't you get wouldn't you get something similar in a passive system with Marangoni flows, like?
I mean, yes. I mean, I guess. Yeah, if you have a flow, but when you say passive system with a Marangoni flow, you're already out of equilibrium. There is some non-stationary state.
But I got a passive fluid. I can have a passive fluid with a gradient in surface tension that is due to the fact that I got a variable contact angle at a gap.
No, I would say the main difference between active systems and passive systems, and it's just that these currents here, they are stationary. And they are steady. But in what you say, you have a passive system, and the Marangoni flow is not stationary. It's a transient. Or, I mean, then you would need to put a source somewhere and a sink somewhere of your chemical. of energy, and then you would have a steady. Yeah, you could. Oh, yeah, okay. No, I agree. Okay, yeah, I agree. I guess you would have something similar. Yeah.
Those simulations are 3D.
No, 2D.
No, this one is okay. And how many particles do you put?
In the liquid gas stuff, there are a lot, like 2 to the 2 times 10 to the 5.
Okay.
But here, when you only want to probe the fluid and the solid, much less, like 10,000.
C'est ça, c'est ça. A question about the size. You have recirculation here.
Mhm.
What is the size? Can you tell us what is the size of the circulation respect to the property of the walls here?
Yes, it's not. It doesn't really depend on the wall. It depends on what we call the run length. What is important, the scale that is important, and that tells you basically how these
Okay. So
currents decay.
U0I
So V naught, so the speed,
time delta tau.
time the
Tau.
tau of changing direction.
So it doesn't depend on the way it's repulsive.
No.
Okay. And second question, does that relate to what is observing with the guy in ESPCI who's doing some micro actimatter things where they see some vortices in a box?
So who? Olivier Dauchot?
Eric Clément.
Ah, Eric Clément. What do you mean it's related?
Well, what they see in their boxes, they see so that the system is going to generate a sort of large swirl, and does it? So in your case, it means that it depends probably on the boundaries.
Yes, but if you're referring to the system that of Eric Clément that he's working with maybe Karine Douarche, what I have in mind is this one of experiments on Escherichia coli and very large hydrodynamics recirculation. Yes. Here, it's different here. In their system, it's different. I mean, it's an active system, but these macroscopic flows, they come from hydrodynamic interactions between the bacteria.
I'm not an experimentalist, but if I were an experimentalist, danger in the lab, what would be the macroscopic quantity that I would see? How does the activity of my fluid would provide me a macroscopic quantity that I could measure if I were an experimentalist?
If I were if I were the experimentalist, I would try. I would try to measure this wetting of bacteria colonies on substrate. I mean, this is try to predict if I know the typical interactions. I think the Graal is if I know the typical interactions between bacteria, between 2 or 3 bacteria, I would like to predict how the colony is going to spread on a substrate, on a given substrate. To me, it would be the experiments, the link that I would do.
How does the activity will affect this?
By the equations, I don't know, but
From a microscopic point of view, I'm having an active fluid.
Yeah,
How
yeah.
does this activity influences the contact angle, or
okay, like that, I don't know. I would need to look more in detail into the equations I get. But,
Ok. Merci beaucoup encore.
Ah merde, désolé, oui,